Before 2017, the dominant approach to sequence modeling relied on recurrent neural networks, or RNNs, and long short-term memory networks. These models possess a severe structural limitation. They factor computation along time steps. To process a sequence, they must generate a hidden state as a function of the previous hidden state and the current input. Because each step depends on the completion of the one before it, the process is locked into O of n sequential operations. You cannot parallelize the training within a single example. As sequence lengths grow, memory constraints severely bottleneck the ability of modern GPU hardware to scale these models. The solution arrived in a 2017 paper titled "Attention is All You Need." Its central thesis was radical: discard recurrence and convolutions entirely. Instead of reading a sequence step by step to build a hidden state, the proposed architecture calculates global dependencies between every input and output simultaneously. This reduces the maximum path length between long-range dependencies to a constant O1 operations. This diagram illustrates the macrostructure of that new model, the transformer. It is split into two distinct pathways. On the left is the encoder stack, and on the right is the decoder stack. To understand how this completely replaces sequential memory, we need to trace the exact mathematical life cycle of a data tensor as it flows through this specific architecture. By translating the temporal problem of language into a geometric one, the transformer converts sequence modeling into an embarrassingly parallel matrix operation, perfectly suited for modern hardware. The process begins with tokenization. An input sequence, like "the animal didn't cross the street because it was too tired," is broken down into distinct units called tokens. Each token is assigned a unique numerical ID from a predefined vocabulary. These discrete IDs are then mapped into a continuous vector space through an embedding layer. Each token becomes a dense, continuous vector of 512 dimensions. By removing the step-by-step recurrent structure, we expose a critical vulnerability. The model now processes all these 512-dimensional vectors simultaneously. It has zero inherent concept of word order. To fix this, the model must artificially inject spatial coordinates directly into the data before any processing begins. This is called positional encoding. The positional encodings are generated using interlocking sine and cosine functions of varying frequencies. The frequency is determined by the token's absolute position in the sequence and its specific dimension indexed. These trigonometric values are then summed directly with the input embedding vectors. This summation embeds a unique, absolute spatial fingerprint into every token. Because for any fixed offset, the position can be represented as a linear function of the previous position. The sequence order is no longer a literal dimension of time. It has been successfully encoded as a continuous mathematical property within the data itself. The encoded vectors now flow into the first sublayer of the encoder, the multi-head self-attention mechanism. Self-attention allows an isolated token to mathematically look at every other position in the sequence to build its own context. This diagram illustrates scaled dot product attention. Isolating the token its vector is multiplied to produce three 64-dimensional vectors: the query, key, and value. To measure alignment, the model computes the dot product of the query against every key. A high dot product value indicates strong mathematical alignment. For example, the query vector for might strongly align with the key vector for animal, producing a large positive number. For large dimensions, dot products can grow enormous in magnitude. This pushes the subsequent softmax function into regions where it has extremely small gradients, which stalls learning. To prevent this, the dot products are scaled. Next, an optional masking step blocks future tokens. A softmax function normalizes these scores into a strict probability distribution. Finally, these weights are multiplied against the value vectors and summed. Information flow is no longer bound by physical proximity in a sentence. Self-attention is a dynamic routing mechanism dictated entirely by learned algebraic alignment. Computing a single weighted average has a drawback. It inherently inhibits the model's ability to focus on different, potentially conflicting relationships simultaneously. This graphic shows the architectural upgrade: MultiHead Attention. Instead of a single attention pass, the base model performs the exact query, key, and value calculations 8 separate times in parallel. Each of these 8 parallel attention layers, or heads, uses different independently learned linear projections for its queries, keys, and values. One attention head might attend strictly to grammatical structure, while a parallel head attends to semantic tone, and another resolves long-range entities. Once all 8 heads compute their outputs, the resulting vectors are concatenated back together into a single wide matrix. To reconcile this, the concatenated output is projected through a final learned weight matrix, returning the tensor to 512 dimensions. MultiHead Attention lets the model jointly extract information from multiple representation subspaces simultaneously. Complex linguistic nuance is preserved, rather than washed out by mathematical averaging. The contextualized output from the attention mechanism now enters the second major sublayer in the encoder block, a position-wise, fully connected feed-forward network. While the attention sublayer routes context between different tokens, the feed-forward network applies the exact same sequence of linear transformations to each token strictly independently. The network projects the 512-dimensional vector up to a massive inner layer of 2048 dimensions. It then applies a nonlinear ReLU activation, allowing only certain signals to pass, before projecting the data back down to 512 dimensions. This architecture diagram shows the critical network infrastructure enabling the stacking of 6 deep layers, residual connections. A residual connection is a shortcut path that allows the input of a layer to bypass that layer and be added directly to its output. Specifically, the output of each sublayer is added directly back to its original input. This shortcut mitigates the vanishing gradient problem, ensuring that early layers still receive sufficient updates during deep network backpropagation. Finally, layer normalization is applied to the summed result. This stabilizes the variance of the activations across the features, making the model less sensitive to its starting weights. Self-attention builds the collective context, but the highly parameterized feed-forward network and its stabilizing residual pathways are what actually refine the isolated representation of each word. We have now reached the very top of the architecture. The final refined tensor is exiting the 6-layer stack of the decoder. This final 512-dimensional vector now contains an incredibly dense, globally informed mathematical representation of the entire sequence context up to that point in time. It passes through a final linear transformation layer, expanding out from 512 dimensions into a massive space corresponding exactly to the model's entire vocabulary size, such as 50,257 dimensions. The resulting numbers at each of these 50,000 nodes are raw, unbounded scores known as logits. A final softmax function evaluates these logits, converting them into a strict probability distribution, where every value falls between 0 and 1, and all values sum to 1. During inference, we apply temperature scaling. Dividing the logits by a temperature scalar of less than 1 physically sharpens the probability curve for highly deterministic output. Conversely, a scalar greater than 1 flattens the curve, making lower probability words more competitive to encourage creative sampling. The final token is then sampled from this distribution. That single token is fed autoregressively back into the bottom of the decoder, and the entire massive matrix operation begins again. The transformer achieved state-of-the-art BLEU scores at a fraction of the computational training cost. BLEU is a metric used to evaluate the quality of text translated by machines against human reference translations. It achieved this strictly because of its architecture. By aggressively stripping out recurrent hidden states, the creators bypassed the constraints of sequential processing entirely. The true legacy of the transformer is mechanical. It proved that the complex, deeply temporal problem of human language could be solved completely through the brute force parallelization of matrix multiplication.